Picture this, a moment so unimaginably ancient that time itself hasn't yet found its rhythm. The universe is less than a second old, a seething ocean of raw energy where temperatures soar beyond 1,000,000 times hotter than the core of our sun. Particles collide and vanish in flashes of light, forces wrestle for dominance, and the very fabric of reality flickers like a candle in a storm. This isn't science fiction, it's the birthplace of everything. The cosmos we know today, with its glittering galaxies and delicate cosmic webs, began as pure chaos, and somehow, against all odds, that chaos forged order. How? That's the mystery we're about to unravel together. Think about the last time you stirred cream into coffee. Watch how the swirls twist and fold, creating fleeting patterns before blending into uniformity. Now scale that up to the size of the universe, where gravity plays the role of the spoon, and the coffee is a primordial soup of particles racing at near light speed. In those first chaotic moments, the universe didn't just expand, it roared into existence, a tempest of energy where even the laws of physics were still taking shape. Yet within that frenzy, tiny irregularities emerged, slight imbalances in the storm. These imperfections, these cosmic wrinkles, would become the seeds of everything: stars, planets, even us. What's truly astonishing is that without that initial turbulence, without those violent beginnings, the universe as we know it couldn't exist. Too much order and matter would have spread too thin, too much chaos, and nothing could have clumped together. It's a razor's edge of probability, a dance of forces so precise that even now, 13.8 billion years later, we're only just beginning to understand how it all fit together. This is the story of how randomness became structure, how disorder sculpted the cosmos, and how the universe, against all odds, found its way from chaos to cosmos. And by the end of this journey, you'll never look at the night sky the same way again. The moment the universe began wasn't just hot, it was a fury beyond comprehension. Imagine squeezing everything that exists, every star, every galaxy, even the empty space between them, into a single point smaller than an atom. That's the singularity where our story starts. Then, in less time than it takes to blink, space didn't just grow, it erupted. This wasn't an explosion into anything because there was no outside. Space itself was stretching, carrying matter and energy along with it like raisins in rising dough. And here's the wild part. For a sliver of time so brief we can barely measure it, the universe expanded faster than light. Not because anything was breaking the rules, but because the rules themselves were being written. In that white-hot frenzy, particles flickered in and out of existence, born from pure energy only to vanish again. The universe was a roiling sea of potential, where even the tiniest quantum fluctuations, random hiccups in the fabric of reality, left lasting marks. Picture tossing a handful of pebbles into a pond. Some ripples cancel each other out, while others merge into bigger waves. Those microscopic wrinkles in the early universe became the gravitational anchors for everything we see today. Without those imperfections, matter would have spread too evenly, and galaxies might never have formed. But here's what's even more mind-bending. The chaos wasn't a flaw, it was essential. A perfectly smooth universe would have stayed that way, cold and empty. Instead, the turbulence of those first moments forged a cosmos rich with structure. The same forces that once sent particles careening wildly now guide planets in their orbits and stars in their slow dances. From that unimaginable heat and violence came the delicate balance that lets galaxies spin and life emerge. It's as if the universe had to scream before it could sing. Now, let's zoom in on one of the most astonishing chapters in cosmic history, a growth spurt so violent it makes the Big Bang look leisurely. In the universe's first trillionth of a trillionth of a trillionth of a second, space didn't just expand, it exploded outward at speeds that defy intuition. This was inflation, a runaway stretching of reality itself, where distances that were once smaller than a proton suddenly became cosmic in scale. Imagine blowing up a balloon to the size of Earth in the time it takes to snap your fingers. Now imagine that happening across every point in the universe simultaneously. What's miraculous about inflation isn't just the speed, but what it left behind. As space stretched, it ironed out the universe's wrinkles, smoothing it like dough rolled thin. That's why when we look at the cosmic microwave background, the afterglow of the Big Bang, it appears nearly uniform in every direction. Without inflation, the universe would look patchy and uneven, like a poorly mixed batter. But here's the twist. While inflation erased large-scale chaos, it magnified the tiniest quantum fluctuations. Those random, microscopic ripples smaller than atoms got stretched across light years, frozen into the fabric of space as subtle variations in density. Think of it like stretching a piece of fabric with tiny ink stains. As the fabric grows, the stains spread and blur, but their faint imprints remain. Those imprints became the cosmic scaffolding regions where gravity could later gather matter into galaxies. Without inflation's dual effect smoothing the overall universe while preserving these crucial imperfections, the cosmos might have remained a featureless void. Yet inflation's brilliance doesn't stop there. It also solves one of the universe's oldest mysteries. Why does space look so similar in all directions? Distant regions of the cosmos, too far apart to have ever interacted, somehow share the same temperature and structure. The answer: before inflation, those regions were close enough to communicate. Inflation then carried them apart faster than light could bridge the gap, preserving their matching properties like twin cities separated by a rising tide. This fleeting moment of hyper-expansion didn't just shape the universe, it made life possible. The same quantum ripples that became galaxies also seeded the formation of stars, planets, and eventually us. It's a humbling thought. The very atoms in your body trace their origins to microscopic trembles in the infant universe, stretched across eternity by inflation's irresistible pull. But inflation isn't just a theory, it's a prediction. Scientists have found its fingerprints in the cosmic microwave background, where slight temperature variations match exactly what inflation would produce. And just last decade, researchers detected primordial gravitational waves, ripples in space-time, that could be echoes of inflation's violent expansion. Each discovery pulls back another layer of the cosmic onion, revealing how chaos and order dance together to build everything we know. So the next time you look up at the night sky, remember, the vast, structured universe we see today was born from a split second of unimaginable transformation. Inflation didn't just stretch space, it wrote the blueprint for reality itself. And somewhere in those quantum ripples, the seeds of your story were already being sown. Even the emptiest void in space isn't truly empty. Thanks to the bizarre rules of quantum mechanics, particles and energy constantly bubble up from nothingness, existing for mere instants before vanishing again. It's as if the universe is a simmering pot with tiny bubbles of reality forming and popping at random. In those first moments after the Big Bang, this quantum froth wasn't just background noise, it was the hidden hand that sculpted the cosmos. Picture a calm lake at night, its surface so still it reflects the stars perfectly. Now imagine a single raindrop disturbing that mirror-like surface, sending ripples outward in perfect circles. In the early universe, quantum fluctuations were those raindrops, tiny, unpredictable disturbances in the fabric of spacetime. But instead of fading away, these ripples were caught in the runaway expansion of inflation, stretched from microscopic quirks into vast cosmic undulations. Regions where particles happened to cluster ever so slightly became denser, while areas with fewer particles thinned out. What started as random flickers became the universe's first rough draft, a blueprint written in the language of gravity. Here's where the magic happens. Over billions of years, gravity acted like a cosmic sculptor, patiently carving structure into the universe. Those slightly denser regions pulled in more matter, growing heavier and attracting even more material in a self-reinforcing cycle. Meanwhile, the thinner areas emptied out, becoming the voids we see between galaxies today. It's a bit like how a gentle slope can channel rainwater into ever deeper channels, eventually carving canyons. But in this case, the water was matter, and the canyons became galaxy clusters millions of light years across. What's astonishing is how delicate this balance was. If quantum fluctuations had been even slightly weaker, gravity might not have had enough starting material to work with, leaving the universe dark and empty. Too strong, and matter could have clumped together too quickly, collapsing into black holes before stars had a chance to form. Instead, the fluctuations were just right, a Goldilocks scenario written into the laws of physics. Scientists can still see echoes of these primordial ripples today. The cosmic microwave background, the oldest light in the universe, shows faint temperature variations that match the pattern of those early quantum fluctuations. It's like finding the fossilized footprints of the universe's first moments. And when astronomers map the distribution of galaxies across billions of light years, they're tracing the grown-up version of those same quantum seeds. The grand cosmic web, with its glittering filaments and vast voids, is the end result of microscopic randomness amplified across cosmic time. This means the galaxies we see, including our own Milky Way, aren't placed randomly. They're the descendants of quantum accidents, the outcome of probabilities playing out on the grandest possible stage. Every star, every planet, every atom in your body exists because of those fleeting particle pairs that appeared and disappeared in the universe's first moments. It's a humbling thought. The same uncertainty that governs subatomic particles also shaped the largest structures in existence. Chaos at the smallest scales gave rise to order on the largest. And this isn't just theoretical. Modern telescopes have measured the distribution of galaxies with incredible precision, revealing a pattern that matches predictions based on quantum fluctuations. Supercomputer simulations can now recreate how those tiny early variations grew into the cosmic web, showing the step-by-step process that turned randomness into structure. It's one of the most profound connections in science, linking the quantum realm to the cosmos itself. So the next time you gaze up at the night sky, remember, the stars aren't just scattered randomly. They're part of an intricate tapestry woven by quantum chance and gravitational patience, a story that began with the faintest whispers of uncertainty and unfolded over billions of years. Without those microscopic fluctuations, the universe might have remained a featureless sea of particles. Instead, it became a place of structure, beauty, and eventually life. For every billion particles of matter that formed in the early universe, there was nearly, but not quite, a matching billion particles of antimatter. This razor-thin difference, this cosmic oversight, is why you and I exist today. In those first microseconds after the Big Bang, matter and antimatter were born in equal amounts, destined to meet and annihilate each other in bursts of pure energy. Left unchecked, that mutual destruction would have left the universe empty, a void with no stars, no planets, just a sea of radiation fading into darkness. But something tilted the scales. Here's the puzzle. Every known physics process we've observed creates matter and antimatter in perfect pairs, like twins born at the same instant. When they meet, they vanish without a trace. So how did matter end up with even the slightest edge? It's as if you flipped a coin 1,000,000,000 times and got heads just once more than tails, a statistical hiccup that shouldn't happen unless the game was rigged. And in this case, the universe was rigged just enough to leave behind a handful of survivors. Scientists call this imbalance baryogenesis, and it's one of the most tantalizing mysteries in physics. The leading theory suggests that in the extreme conditions of the early universe, certain rare particles decayed unevenly, producing slightly more matter than antimatter. Imagine a factory making two types of shoes, left and right, but due to a tiny flaw in the machinery, for every 1,000,000 pairs, one extra left shoe slips through. Over time, those leftovers pile up. In the cosmos, those leftover particles became the raw material for everything we see. But here's where it gets even stranger. The imbalance wasn't just random luck. It might have been written into the laws of physics themselves. Experiments at particle colliders have found hints that some fundamental forces, like the weak nuclear force, treat matter and antimatter slightly differently. It's as if the universe has a hidden preference, a subtle bias coded into its DNA. Without that bias, the grand annihilation would have left nothing behind. What's truly humbling is how precarious our existence is. If the imbalance had been even a fraction smaller, the universe might not have had enough matter left to form galaxies. Too much, and the excess could have collapsed into black holes before stars had a chance to ignite. Instead, the numbers lined up just right, allowing gravity to gather those scattered particles into clouds, then stars, then planets, building blocks for the story of life. And the mystery isn't just academic. Understanding why matter won out could reveal deeper truths about the universe's structure. Some physicists speculate that antimatter-dominated regions might exist somewhere in the cosmos, invisible to us because any contact between our matter and their antimatter would be catastrophic. Others think the answer lies in undiscovered particles or forces that acted only in those first moments. Every time scientists recreate early universe conditions in particle colliders, they're hunting for clues to this cosmic imbalance. So far, the evidence is maddeningly faint, like trying to reconstruct a symphony from a single note. But each experiment brings us closer to answering a question that's literally existential. Why is there something rather than nothing? So the next time you hold a piece of fruit or feel the weight of a book in your hands, remember, you're holding the remnants of an ancient victory, the survivors of a battle between matter and antimatter that shaped everything. The universe could have been empty. Instead, thanks to a whisper of asymmetry, it's full of wonders, and somewhere in that mystery lies the key to our very existence. Before atoms could exist, before stars could ignite, the universe had to endure a phase so extreme it defies imagination. A time when matter wasn't solid, liquid, or even gas, but a seething plasma so hot that the very building blocks of reality swam freely. This was the Quark-Gluon Plasma, a primordial soup where temperatures exceeded 4 trillion degrees, far hotter than any furnace in the cosmos today. In this chaotic state, quarks, the smallest known pieces of matter, darted like frenzied fireflies, while gluons, the particles that carry the strong nuclear force, buzzed between them like invisible glue. Nothing could stick, no protons, no neutrons, just an untamed ocean of raw potential. But then, something remarkable happened. As the universe expanded, it cooled, not slowly, but at a pace so rapid it would make your head spin. Within microseconds, the temperature dropped enough for gluons to finally do their job. Think of it like a crowd of people in a scorching desert suddenly finding shade. The quarks, once too energetic to bond, began pairing up two up quarks and one down quark forming a proton, two downs and one up forming a neutron. This was the moment matter as we know it began taking shape. What's astonishing is how delicate this transition was. If the universe had cooled even slightly faster, quarks might have frozen into bizarre, unstable configurations. Too slow, and the plasma could have lingered, delaying the formation of atoms indefinitely. Instead, conditions lined up perfectly, allowing the first protons and neutrons to emerge like islands in a receding flood. And these weren't just any particles, they were the seeds of hydrogen and helium, the universe's first elements. Here's where it gets even wilder. For a brief window, this Quark-Gluon Plasma wasn't just a theoretical idea, it was recreatable. In massive particle colliders like the Large Hadron Collider, scientists have smashed atoms together with such force that they momentarily resurrect this primordial state. The results, a fleeting glimpse into the universe's first moments, where matter behaves more like a liquid than a gas, flowing with near-perfect frictionlessness. It's as if we've built a time machine not for visiting dinosaurs, but for touching the fabric of reality itself. Yet this plasma's true legacy lies in what it left behind. Every proton in your body, every neutron in the air you breathe, is a direct descendant of that chaotic soup. The iron in your blood, the oxygen in your lungs, all of it traces back to quarks that once raced freely until the universe cooled just enough to trap them in atomic nuclei. And that trapping wasn't just random. The same strong nuclear force that bound those first protons and neutrons still holds your atoms together today, a cosmic handshake spanning billions of years. But the story doesn't end there. Those early protons and neutrons faced another hurdle, surviving the universe's next violent phase. Within minutes, they began fusing in the fires of Big Bang Nucleosynthesis, forming deuterium, helium, and trace amounts of lithium. It was the universe's first attempt at chemistry, a trial run that set the stage for everything to come. Without that Quark-Gluon Plasma cooling at just the right moment, none of those reactions could have occurred. No elements, no stars, no planets, just a thin, lifeless mist of particles drifting through eternity. So the next time you look at your hand, remember, you're holding a piece of the universe's wildest era. The same quarks that once danced freely in a 4 trillion degree plasma now sit quietly in your cells, tamed by time and temperature into the architecture of life. From chaos to cosmos, indeed. The universe was only 3 minutes old when the first true alchemy began. With temperatures still blistering at over 1 billion degrees, protons and neutrons freshly forged from the Quark-Gluon Plasma finally had a chance to bond. But this wasn't chemistry as we know it, no gentle reactions or balanced equations. This was nucleosynthesis at its most primal, a violent ballet of particles colliding with enough force to overcome their natural repulsion. Every second counted. The universe was expanding so rapidly that this window for element building would slam shut almost as quickly as it opened. Picture a frenzied marketplace where traders only have minutes to barter before the doors close forever. Protons, the bare nuclei of hydrogen, were the currency. Some snatched passing neutrons to form deuterium, a heavy hydrogen isotope. Others, moving just fast enough to overcome electrostatic repulsion, fused into helium nuclei. Trace amounts of lithium and beryllium flickered into existence, only to be torn apart again by the intense heat. It was a delicate dance, too slow, and expansion would dilute the particles too much, too fast, and heavier elements might have formed prematurely, choking the universe's future potential. What's staggering is how much hung in the balance during those 3 minutes. Nearly all the hydrogen in the cosmos today, every molecule in water, every wisp of interstellar gas, dates back to this fleeting moment. The helium forged then still fueled stars, making up about 25% of the universe's ordinary matter, and yet the process left behind almost nothing heavier. No carbon for life, no oxygen for water, no iron for planets, just the lightest elements scribbled like a hasty signature across the cosmos. Scientists call this Big Bang Nucleosynthesis, and its predictions match reality with eerie precision. The observed ratios of hydrogen to helium in ancient stars, dead on. The trace amounts of lithium detected in primordial gas clouds, exactly as calculated. It's as if we've found the universe's recipe book frozen in time. But here's the twist: these elements weren't just scattered randomly. Quantum fluctuations from inflation had already imprinted the cosmos with slight density variations. So where matter was marginally denser, nucleosynthesis ran slightly hotter, leaving behind subtle chemical fingerprints. This process also solved one of cosmology's early puzzles. In the 1940s, physicists realized that if all matter had formed in stars, the universe wouldn't have nearly enough helium. The answer: most helium wasn't made in stars at all. It was forged in those first 3 minutes, a relic of the universe's infancy. Even now, when astronomers analyze the light from quasars billions of light years away, they're seeing absorption lines that match Big Bang nucleosynthesis predictions with pinpoint accuracy. Yet this triumph of creation came with a catch. The newborn universe was still too hot for atoms to form. Electrons raced freely through the plasma, scattering photons in a dense fog. For nearly 400,000 years, the cosmos remained opaque, a glowing soup of ionized gas. Only when expansion cooled the universe enough for electrons to settle into orbit around nuclei forming neutral atoms did light finally break free. That moment, the release of the cosmic microwave background radiation, is the earliest picture we have of the universe. And etched into that afterglow are the elemental abundances cooked up during nucleosynthesis, a time capsule from the universe's first act of craftsmanship. But perhaps the most profound legacy of those 3 minutes is what they made possible. Without that initial hydrogen and helium, gravity would have had nothing to gather into stars. No stars meant no heavier elements, no planets, no ingredients for life. The universe would have remained a dark, featureless expanse. Instead, those first elements became the kindling for cosmic structure, the raw materials for everything that followed. Every mountain, every ocean, every breath you take contains atoms that began their journey in those frantic, fiery moments. So the next time you see a child's helium balloon float skyward, remember, that gas is older than the stars. It's a living relic of the universe's first great synthesis, a whisper from a time when all existence could fit into a single, unimaginably hot point. And somehow, against all odds, that chaos gave rise to the elements that would one day weave the tapestry of life. The universe took its first breath and then fell silent. For nearly 400,000 years after the Big Bang's afterglow faded, space became a shadowy expanse where no stars twinkled, no galaxies spiraled, just an endless sea of hydrogen gas so pristine you could swim through it for millions of light years without touching a single dust grain. This was the cosmic dark ages, a chapter so quiet and unremarkable that if you'd been there, you might have thought nothing was happening at all. But beneath that stillness, gravity was working its slow magic, pulling matter into hidden patterns that would one day blaze with light. Imagine walking through a forest at night, listening for the faintest rustle of leaves. That's what astronomers do when they study this era. The only light came from the cosmic microwave background, stretched by expansion into invisible radio waves, while the hydrogen itself absorbed what little radiation passed through it. Space wasn't just dark, it was cold, cooling to temperatures barely above absolute zero. Yet even in that frigid blackness, tiny fluctuations left over from inflation were gathering strength. Regions slightly denser than their surroundings pulled in more gas, growing heavier, while emptier patches became voids. It was a cosmic game of hide and seek where the seekers moved at the speed of gravity, painfully slow by universe standards. What's fascinating is how fragile this balance was. Too much early structure, and hydrogen might have collapsed into massive black holes before stars could form. Too little, and the gas could have remained diffuse forever. Instead, the universe threaded the needle, letting gravity work just fast enough to prepare the stage for its next act. And here's the kicker: we can actually hear echoes of this era. The hydrogen of the Dark Ages absorbed specific wavelengths of background radiation, leaving faint dips in radio telescope data, like finding fossilized ripples in a pond that's long since stilled. But the real drama was happening in the shadows. As hydrogen pooled into vast, invisible clouds, the first proto-galaxies began taking shape, a dark matter scaffolding draped with gas waiting for a spark. The universe was a coiled spring holding its breath, and then, somewhere in the darkness, a pocket of gas grew dense enough to ignite. The cosmic dawn was coming, a sunrise that would forever change the cosmos. This quiet epoch might seem like a footnote in the universe's story, but it's the reason we're here. Without those hundreds of millions of years of patient gathering, matter might never have clumped densely enough to birth stars. No stars meant no heavy elements, no planets, no chemistry complex enough for life. The Dark Ages weren't empty, they were the universe's deepest workshop, where gravity labored in silence to build the foundations of everything we know. And when the first star finally flickered to life, it didn't just light up the cosmos, it lit the fuse for a chain reaction that would eventually lead to galaxies, planets, and us. Deep in the cosmic dark, where hydrogen clouds had gathered for hundreds of millions of years, something extraordinary finally happened. Gravity, patient and relentless, overcame the last resistance. A knot of gas compressed to unimaginable density reached a critical threshold. At its core, temperatures soared past 10 million degrees, and in that searing instant, nuclear fusion ignited. The universe, for the first time, welcomed starlight. These weren't just any stars. Born from pure hydrogen and helium, the only elements available, they grew to sizes that dwarf anything in our modern night sky. Imagine behemoths 200 times the mass of our sun, burning with a brilliance that could outshine entire galaxies of today's stars. But such glory came at a cost. Their colossal size meant they lived fast and died young, exhausting their fuel in mere millions of years. A cosmic blink compared to the 10 billion-year lifespan of stars like our sun. Inside these titans, the alchemy of the cosmos took its first real steps. Under crushing pressures and temperatures hotter than anything since the Big Bang, hydrogen nuclei fused not just into helium, but further into carbon, oxygen, and even traces of heavier elements. Each reaction released energy, yes, but also something far more precious, the raw materials for everything that would follow. For the first time, the universe wasn't just recycling its original ingredients, it was cooking new ones. Yet their greatest contribution came in death. When these first stars finally exhausted their fuel, their cores collapsed catastrophically, triggering supernovas so violent they would make modern star explosions look like firecrackers. In those final moments, temperatures reached billions of degrees, forging elements like silicon, iron, and gold in a matter of seconds. Then, like cosmic gardeners, the explosions scattered these heavy elements across interstellar space, enriching the surrounding gas clouds with the building blocks of planets and life. We're only beginning to piece together their story. Unlike modern stars, which often form in clusters, the first stars may have risen in isolation, each a lonely beacon in an otherwise dark universe. Their light, long since faded, remains beyond the reach of even our most powerful telescopes. But we've found indirect clues, ancient quasars whose light has traveled nearly 13 billion years to reach us, show traces of elements that could only have come from these primordial giants. Computer simulations recreate their likely appearance: bluish-white monsters, free of planetary systems, their skies unadorned by even a single speck of dust. What's humbling is how deeply their legacy runs through us. The iron in your blood, the calcium in your bones, atoms forged in those first stellar furnaces or their explosive deaths. Every piece of Earth, every rocky planet in the cosmos, owes its existence to the fact that these stars lived fast, died young, and gifted the universe with something it had never known before: complexity. And they didn't just change the universe's chemistry, they changed its very structure. Their ultraviolet radiation began ionizing the surrounding hydrogen, carving bubbles of transparency in the foggy darkness. This marked the beginning of the Epoch of Reionization, a transformative era when light finally broke free to travel across the cosmos. Without these pioneers, the universe might have remained forever shrouded in mist, its potential locked away. So when you look up at the night sky, remember, those twinkling points of light are the descendants of giants. The first stars were the match that lit the cosmic fuse, turning a universe of simple gases into one rich with possibilities. And somewhere in that chain of stellar births and deaths, the seeds of your existence were sown. Galaxies didn't just emerge fully formed, they grew, evolved, and transformed through processes as dynamic as life itself. Picture the early universe as a vast, dark canvas where gravity began tracing its first strokes. Those slight overdensities left by quantum fluctuations in the Big Bang's aftermath became gathering points, pulling in streams of hydrogen like rivers feeding a lake. Over hundreds of millions of years, these pools of gas condensed into swirling disks and glowing spheres, each one a newborn galaxy taking its first breath. Our Milky Way wasn't always the grand spiral we know today. In its youth, it was smaller, hungrier, and far more aggressive. Like a cosmic predator, it absorbed dozens of smaller satellite galaxies, stretching their stars into elongated streams that still orbit invisibly around us. One of its most dramatic meals, a galaxy called Gaia Enceladus, was devoured around 9 billion years ago, leaving behind a halo of stars that moved backward compared to the rest of the Milky Way. These galactic mergers weren't gentle. Imagine two crowds of people walking into each other from opposite directions. Individual stars rarely collide, but their paths twist into new orbits, reshaping the entire structure. Collisions between galaxies are some of the most breathtaking events in the cosmos. When the Antennae galaxies, two spirals about 45 million light-years away, began merging, their gravity stretched them into long, luminous tails resembling insect antennae. Inside those chaotic swirls, clouds of gas collided, igniting bursts of star formation so intense they could be seen across intergalactic space. But this violence isn't destruction, it's rebirth. Without such mergers, many galaxies would run out of the fresh gas needed to create new stars. The cosmic dance of colliding galaxies isn't an ending, it's how the universe keeps its stellar nursery stocked. Yet not all galaxies follow the same blueprint. Some, like our Milky Way, settled into elegant spirals with star-filled arms winding around brilliant cores. Others became featureless ellipsoids, smooth, egg-shaped collections of ancient stars where little new light has been born for billions of years. And then there are the irregulars, misshapen galactic leftovers that avoided collisions or simply never grew large enough to settle into a defined form. Each type tells a story about its past. Ellipticals often bear the scars of violent mergers, while spirals like ours enjoyed relatively peaceful growth. their delicate structures preserved by isolation. At the heart of nearly every large galaxy lies one of the universe's most enigmatic objects, a supermassive black hole. These aren't the destructive monsters science fiction portrays, but gravitational anchors that shape their galaxies in subtle ways. The Milky Way's own Sagittarius A, with 4 million times the Sun's mass, is surprisingly quiet today. But in the past, it may have been an active quasar, its intense radiation and powerful jets heating surrounding gas and regulating star formation. This feedback loop, where a black hole's activity can stunt its galaxy's growth, is one of nature's most fascinating balancing acts. Too active, and stars lose the gas they need to form. Too quiet, and the galaxy might overproduce stars, exhausting its fuel too quickly. Galaxies also communicate in ways we're only beginning to understand. The spaces between them aren't truly empty, but filled with thin filaments of gas, cosmic highways along which matter flows. Some galaxies, like our neighbor Andromeda, are still growing by siphoning gas from these intergalactic streams. Others, trapped in dense clusters, have their gas stripped away by the hot plasma that fills those regions, leaving them red and dead, packed with aging stars but unable to birth new ones. It's a reminder that a galaxy's environment shapes its destiny as much as its internal dynamics. What's astonishing is how deeply our existence is tied to these grand structures. The heavy elements forged in early generations of stars, elements necessary for planets and life, were mixed into the galactic disk by countless rotations, eventually finding their way into nebulae where new stars like our Sun formed. Every atom in your body was recycled through multiple stellar lifetimes, each cycle occurring within the safe harbor of a stable galaxy. Without these islands of matter, the universe might have remained a diffuse, unbroken sea of hydrogen, never dense enough to spark the complexity that leads to life. So when you gaze at the Milky Way's faint band of light stretching across the night sky, you're not just seeing stars, you're witnessing the legacy of billions of years of galactic evolution. A story of mergers and transformations, of black holes and spiral arms, all woven together by gravity into the cosmic tapestry we call home. And somewhere in that tapestry, among the countless stars and swirling gas, our tiny corner of the universe found the perfect conditions to ask how it all began. Black holes aren't just cosmic vacuum cleaners, they're master sculptors, shaping galaxies with invisible hands. Take the supermassive black hole at the center of our Milky Way, Sagittarius A. While it may seem like a sleeping giant now, its gravitational influence stretches far beyond its event horizon. Like an unseen conductor, it orchestrates the motion of thousands of stars, forcing them into dizzying orbits at speeds exceeding 5,000 kilometers per second. These aren't random dances, they're precise celestial ballets, revealing how even light years away, a black hole's pull dictates the rhythm of an entire galaxy. But their power isn't limited to gravity alone. When black holes feed, they transform matter into energy with terrifying efficiency. While nuclear fusion in stars converts less than 1% of mass into energy, a spinning black hole's accretion disk can approach 40% efficiency, making them the universe's ultimate power plants. The energy released isn't gentle either. Jets of plasma, accelerated to nearly light speed, erupt from the poles of active black holes, stretching hundreds of thousands of light years across intergalactic space. These aren't just pretty light shows, they're cosmic blowtorches, heating surrounding gas so intensely that entire galaxy clusters can be sterilized of star-forming material. Yet paradoxically, these same destructive forces can spark creation. The quasar 3C273, 9 billion light-years away, blasts out enough energy in 1 second to power human civilization for 20 trillion years. But within that maelstrom, shockwaves compress surrounding gas clouds, triggering waves of star formation in their wake. It's as if the universe built a machine where destruction and creation share the same engine, where chaos itself becomes the architect of structure. Even stranger are the supermassive black holes that somehow grew too fast. In the early universe, astronomers have found black holes with billions of solar masses, monsters that theoretically shouldn't have had enough time to form. One leading hypothesis suggests they grew from direct collapse, where entire gas clouds bypassed the star stage entirely, imploding straight into black hole singularities. These primordial giants may have served as gravitational anchors, accelerating galaxy formation by providing ready-made hearts for swirling proto-galaxies to coalesce around. We're only beginning to understand their full role. Recent simulations show that without black hole feedback, those powerful jets and radiation outbursts, galaxies would form stars too rapidly, burning through their fuel and leaving the universe filled with small, stunted galaxies. Instead, black holes act as cosmic regulators, their outbursts preventing runaway star formation while enriching intergalactic space with heavy elements. The gold in your jewelry might have been forged in the accretion disk of a black hole before being flung across space by these very jets. What's most humbling is how these extreme objects connect to everyday reality. The same physics that governs a black hole's appetite also explains why your GPS needs relativity corrections to stay accurate. The warping of space-time isn't just some distant phenomenon, it's a fundamental feature of our universe, written into the fabric of existence itself. From the smallest scales to the largest, black holes remind us that chaos and order aren't opposites, they're partners in the cosmic dance, forever shaping the universe in ways we're only beginning to comprehend. Imagine a spiderweb glistening with dew at dawn, each droplet clinging to strands you can barely see. That's our universe. The stars, galaxies, and planets are the visible beads of moisture, but the web itself, the hidden structure holding everything together, is dark matter. We can't see it, touch it, or even detect it directly, yet its gravitational embrace is the reason galaxies spin as fast as they do without flying apart. Without this invisible scaffold, the cosmos as we know it wouldn't exist. Here's the puzzle. When astronomers first measured the rotation speeds of galaxies in the 1930s, they expected stars on the outer edges to move slower, just as Pluto orbits the Sun more sluggishly than Mercury. Instead, they found stars racing at nearly the same speed regardless of distance, as if some unseen mass was anchoring them in place. The math was undeniable. For every gram of visible matter, stars, gas, planets, there had to be at least 5 grams of something else, something that neither emits nor reflects light. They called it dark matter, and its fingerprints are everywhere. Clusters of galaxies behave like cosmic wrecking balls, their gravity bending light from objects behind them in a phenomenon called gravitational lensing. But the amount of bending observed is far stronger than what visible matter alone could produce. It's as if you saw a shadow cast by an invisible giant, warping the fabric of space-time itself. Even the cosmic microwave background, the afterglow of the Big Bang, bears the imprint of dark matter's gravitational tug, its subtle temperature variations revealing how this mysterious substance shaped the early universe. The leading theory suggests dark matter consists of weakly interacting massive particles, hypothetical entities that barely interact with normal matter except through gravity. Picture a crowd of ghosts walking through a busy street, unseen and unfelt, yet their collective weight could tilt a scale. Scientists have built detectors deep underground, shielded from cosmic noise, hoping to catch even a single WIMP collision with ordinary atoms. So far, silence. Other candidates include actions ultralight particles that could flutter through Earth like a quantum breeze, or even primordial black holes forged in the universe's first second. Yet dark matter's stubborn invisibility isn't just a technical hurdle, it's a cosmic irony. This substance outnumbers ordinary matter 5 to 1, yet it remains as elusive as a whisper in a hurricane. Some theories propose we've been looking at gravity all wrong, that dark matter doesn't exist, and instead, our understanding of physics needs a radical rewrite. But the evidence piles up, from the way galaxies rotate to how they clump together in vast superclusters. Dark matter's gravitational signature is written across the sky. What's truly humbling is how much we owe to this enigma. In the early universe, dark matter acted as a gravitational blueprint, its subtle overdensities attracting hydrogen gas to form the first proto-galaxies. Without it, stars might never have ignited, and the cosmic web, the sprawling network of filaments connecting galaxy clusters, wouldn't have its intricate architecture. Even now, as you read this, rivers of dark matter flow through your body, their gravity subtly shaping the destiny of galaxies millions of light years away. Solving this mystery wouldn't just fill a gap in our textbooks, it could unveil entirely new laws of nature. Perhaps dark matter is a portal to a hidden sector of particles, or evidence of extra dimensions curled tighter than an atom. One thing's certain, the universe has been holding its greatest secret in plain sight, written not in light but in the silent pull of gravity. And when we finally decode it, we won't just understand dark matter, we'll understand the invisible threads weaving the cosmos together. Just when cosmologists thought they had the universe figured out, it threw them a curveball. In the late 1990s, two teams of astronomers made a discovery that turned astrophysics on its head. The universe wasn't just expanding, it was accelerating. Galaxies weren't merely drifting apart like leaves on a pond. They were being pushed apart by some unseen force, growing more distant at ever-increasing speeds. This wasn't just unexpected, it defied everything we knew about gravity. The culprit, a mysterious phenomenon called dark energy. Think of it like this. If the universe were a loaf of raisin bread baking in an oven, you'd expect the expansion to slow as the dough stretches. The raisin's galaxies moving apart gradually as the energy from the initial kneading, the Big Bang, dissipates. But dark energy is like someone turning up the oven mid-bake, making the dough expand faster and faster. Unlike gravity, which pulls matter together, dark energy seems to be a property of space itself, a kind of anti-gravity woven into the fabric of the cosmos. What's truly bizarre is how late this acceleration started. For the first 9 billion years after the Big Bang, gravity had the upper hand, slowing the expansion as matter clumped into galaxies and clusters. Then, around 5 billion years ago, dark energy took over. Suddenly, the universe shifted gears, as if an invisible foot had pressed down on the cosmic gas pedal. Today, dark energy makes up nearly 70% of the universe's total energy budget, dwarfing both ordinary matter and dark matter. Yet we have no idea what it actually is. The leading theory suggests dark energy might be the cosmological constant, an energy inherent to empty space first proposed by Einstein, then discarded as his greatest blunder. Quantum physics tells us that even a perfect vacuum isn't truly empty. It crackles with virtual particles popping in and out of existence. Could this quantum froth be the source of dark energy's push? Maybe, but when physicists calculate how strong this effect should be, their numbers overshoot observations by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in science history. Another possibility is that dark energy isn't constant at all, but a dynamic field that changes over time, dubbed quintessence. Ancient philosophers used this term for the fifth element beyond earth, air, fire, and water, a poetic fit for something so elusive. If true, dark energy's strength could fluctuate, potentially leading to a future where it tears atoms apart or even rips spacetime itself. The stakes couldn't be higher. Dark energy doesn't just accelerate expansion, it writes the universe's final chapter. If it continues unchecked, distant galaxies will eventually vanish beyond our cosmic horizon, their light stretched to wavelengths too long to detect. Star formation will cease as gas clouds are pulled apart, leaving galaxies isolated and dark. Given enough time, even atoms might be torn asunder in a big rip. Alternatively, dark energy could decay, allowing gravity to regain control in a big crunch. Or perhaps something even stranger awaits, a phase transition where the vacuum of space itself becomes unstable, rewriting the laws of physics in an instant. For now, telescopes like Euclid and the Vera Rubin Observatory are mapping billions of galaxies to trace dark energy's influence across cosmic time. Each new observation peels back another layer of the mystery. One thing's certain, dark energy isn't just another puzzle, it's a reminder that the universe still holds profound surprises. And unlocking its secrets might reveal not just the fate of the cosmos, but entirely new laws of nature hiding in plain sight. Zoom out far enough, and the universe reveals its true structure, not random scattering, but an intricate network of luminous threads weaving through the void. This is the cosmic web, a vast architecture of galaxies strung along filaments of dark matter like pearls on an invisible necklace. Each filament stretches hundreds of millions of light years, connecting galaxy clusters at their intersections in a pattern so grand it makes the largest superclusters look like knots in a spider's silk. What's astonishing is how perfectly this mirrors the predictions of supercomputer simulations. When scientists model the universe's growth, starting with tiny quantum fluctuations from the Big Bang and letting gravity work over billions of years, the result looks eerily familiar, a web of matter mirroring the one we observe through telescopes. The Sloan Digital Sky Survey, which mapped millions of galaxies, showed this structure in stunning detail. Galaxies huddled along delicate strands, with yawning voids between them so empty you could travel 100 million light-years without encountering a single star. These filaments aren't just pretty patterns, they're cosmic highways. Gas flows along them like water through pipes, feeding growing galaxies at the nodes where threads intersect. The Perseus-Pisces supercluster, one of the nearest filaments to us, funnels material into galaxies at a rate that would fill 1,000 suns every year. Meanwhile, the voids between filaments aren't just empty, they're underdense regions where space itself expands slightly faster, as if the universe is pushing matter toward the busy intersections. Dark matter is the unseen architect of this web. Its gravity drew ordinary matter into these threads early on, with hydrogen gas following the dark scaffolding like iron filings aligning to a magnet. Even now, galaxies along filaments move in coherent streams, a phenomenon called galactic infall, where whole groups spiral toward massive clusters like the Great Attractor, a gravitational anomaly pulling millions of galaxies toward the Hydra-Centaurus supercluster. But the cosmic web isn't static. It breathes and evolves. Collisions between filaments send shockwaves through intergalactic gas, heating it to millions of degrees and creating some of the hottest plasma in the universe. The Spiderweb Galaxy, a protocluster 7 billion light-years away, shows this process in action. Dozens of young galaxies swarming like fireflies at a filament crossroads, their gravity weaving them into a single colossal structure. What's humbling is how this grand design connects to us. The Milky Way resides in a filament called the Laniakea supercluster, 100,000 galaxies all flowing toward the same cosmic watershed. Our local patch of the web might seem ordinary, but it's part of a tapestry stretching across the observable universe, a reminder that even in the vastness of space, everything is connected by threads older than time. Superclusters are the universe's grandest neighborhoods, colossal gatherings of galaxy clusters, so vast they make even the Milky Way feel like a speck of dust in a swirling metropolis. Picture a city where each building is a galaxy cluster containing thousands of galaxies, and the entire skyline stretches over 500 million light-years. That's the scale we're talking about. Our own galactic home, the Milky Way, is just one resident of the Laniakea supercluster, a sprawling megastructure that contains roughly 100,000 galaxies, all drifting together through the cosmic void like leaves caught in the same gentle current. But what holds these titanic assemblies together? Gravity, once again, is the invisible architect, but not just any gravity. Superclusters form where the thickest filaments of the cosmic web intersect, creating gravitational wells so deep they pull in entire clusters over billions of years. The Great Attractor, a mysterious region hidden behind the dust of our own galaxy, acts like a cosmic whirlpool, drawing the Milky Way and countless other galaxies toward it at over 600 kilometers per second. Yet even this immense pull is just a small part of Laniakea's broader flow, a slow-motion river of galaxies moving toward an even larger concentration of mass called the Shapley supercluster. Superclusters aren't just bigger versions of galaxy clusters, they're fundamentally different. While clusters are bound tightly by gravity, superclusters are more like loose federations, their member clusters still drifting apart as the universe expands. They're transient giants, destined to stretch and thin over time rather than collapse into single structures. The Hercules Corona Borealis Great Wall, one of the largest superclusters ever observed, spans 10 billion light-years, a staggering 7% of the observable universe's diameter. But even this behemoth isn't a single, cohesive object. It's a web of galaxies strung along filaments, a cosmic archipelago in an ever-growing sea of space. What's fascinating is how these structures reveal the limits of cosmic organization. Superclusters represent the final rung on the ladder, the largest scale where matter still clumps together under gravity's influence. Zoom out any further and the universe starts to look uniform, its matter distributed evenly across the vast expanse. That transition from intricate web to smooth homogeneity is one of cosmology's most profound realizations. No matter how big the structures we find, the universe itself is always larger, always more expansive than our tools can fully capture. And yet, for all their grandeur, superclusters are also deeply personal. The atoms in your body were forged in stars that formed because of the gravitational tug of structures like Laniakea. The same forces that shaped these cosmic cities also shaped the conditions that allowed life to emerge. So when you look up at the night sky, remember, you're not just a resident of Earth or the Milky Way. You're a citizen of a supercluster, part of a story written in gravity and starlight, stretching across hundreds of millions of light-years. The faintest whisper from the dawn of time still lingers in the depths of space, not as starlight, but as a ghostly glow of microwaves bathing the entire universe. This is the cosmic microwave background. The afterglow of the Big Bang stretched and cooled over 13.8 billion years into a faint radio hum just 3 degrees above absolute zero. It's the oldest light we can see, a snapshot of the universe as it was 380,000 years after its birth, when the first atoms formed and photons finally broke free from the primordial plasma. What makes this glow extraordinary isn't just its age, it's the story written in its subtle imperfections. To the naked eye, the cosmic microwave background appears uniform, like static on an old television screen. But precise measurements reveal temperature variations as tiny as 1 part in 100,000, hotter and colder patches no larger than 1/10 of a degree. These aren't random fluctuations, they're cosmic fossils. the imprints of density variations from when the universe was younger than a human heartbeat. The slightly denser regions where matter had clumped ever so slightly would become the gravitational seeds for galaxies and clusters, while the cooler, emptier patches would grow into the vast voids between them. Capturing this ancient light required instruments of staggering sensitivity. The COBE satellite in the 1990s first mapped these variations, followed by WMAP and Planck, which refined the measurements to exquisite detail. What they found was a perfect match for predictions. The pattern of hot and cold spots aligned precisely with what inflation theory suggested. It was as if we'd discovered the universe's baby pictures, complete with the first hints of its future structure. But the cosmic microwave background isn't just a relic, it's a Rosetta Stone for cosmology. By analyzing its polarization, the slight directional preference of its light waves, scientists have detected evidence of primordial gravitational waves, ripples in spacetime from the universe's first trillionth of a second. These waves, if confirmed, would be smoking gun evidence for inflation, the explosive expansion that set the stage for everything to come. Perhaps most remarkably, this glow connects directly to our existence. The same density variations that seeded galaxies also determined where stars would eventually form, where planets would coalesce, and where billions of years later life might emerge. When you tune an old radio between stations, about 1% of the static you hear is literally the echo of creation, the remnant radiation from the universe's fiery birth. Today, the cosmic microwave background continues to reveal surprises. Anomalies like the cold spot, a strangely large cool region, hint at possible structures beyond our observable universe or even exotic physics we've yet to understand. Each new observation peels back another layer, reminding us that the universe's first light still has stories to tell. And as future telescopes probe even deeper, we may yet decode whispers from a time before atoms, before light, when all existence was a seething quantum froth waiting to unfold. Einstein predicted them a century ago, but it took until 2015 for humanity to finally catch a gravitational wave, a ripple in the fabric of spacetime itself. These waves aren't like light or sound. They don't travel through space, they are space, stretching and squeezing the very dimensions we exist in as they pass. Picture dropping a pebble into a pond. The ripples spread outward, distorting the water's surface. Now imagine that pond is reality, and the pebble is something unimaginably massive, like two black holes spiraling into each other at half the speed of light. That's the kind of event that sends gravitational waves echoing across the cosmos. The first detection came from LIGO, the Laser Interferometer Gravitational Wave Observatory, a pair of facilities in the U.S. with laser beams running through 4-kilometer-long tunnels. When the wave from that black hole collision passed through Earth, it altered the length of one tunnel by less than 1,000th the width of a proton, a change so small it defies belief. Yet LIGO exquisitely tuned instruments caught it, marking the dawn of an entirely new way to study the universe. Until then, astronomy had relied on light, visible, radio, X-rays, but gravitational waves let us listen to the cosmos, hearing events no telescope could ever see. What's astonishing is what these waves reveal. When two neutron stars collided in 2017, the resulting gravitational waves carried signatures of their crushing density and the exotic physics at their cores. Telescopes scrambled to observe the aftermath, catching the glow of heavy elements like gold and platinum forged in the explosion. For the first time, we had both the sound and the sight of a cosmic cataclysm, a multi-messenger event that opened a new chapter in astrophysics. But gravitational waves aren't just about violent mergers, they're also time machines. the further we detect them from, the closer we get to the universe's infancy. Future observatories like the space-based LISA mission could catch waves from the mergers of supermassive black holes in the early universe, or even remnants of cosmic inflation echoes from the first trillionth of a second after the Big Bang. It's like finding a recording of the universe's first heartbeat, a whisper from the moment reality itself began unfolding. And here's the wildest part: these waves don't just carry information, they are information. Every ripple encodes the masses, spins, and energies of the objects that created it. A single detection can tell us how black holes form, whether neutron stars are made of Quark-Gluon Plasma, or if gravity behaves exactly as Einstein predicted under extreme conditions. They're cosmic telegrams delivering secrets from the most hidden corners of existence. So while telescopes show us the universe's face, gravitational waves let us feel its pulse. And with every new detection, we're not just observing history, we're touching the invisible threads that weave it together. What if everything we know, every galaxy, every star, every law of physics, is just one tiny bubble in an infinite cosmic froth? This is the startling premise of multiverse theory, the idea that our universe might be one of countless others, each with its own unique rules and realities. Picture a vast ocean where each wave crest is a separate universe, some shimmering with familiar stars, others frozen in darkness or crackling with alien physics where gravity repels and time runs backward. The chaos of the Big Bang, rather than a single explosive beginning, could have been a cosmic branching point, a moment when reality fractured into infinite variations, each carrying a different destiny. The math behind this isn't just speculative fiction. Inflation theory, which explains the universe's rapid early expansion, suggests that some regions of space might have stopped inflating while others continued, creating isolated pocket universes with varying properties. String theory, another framework attempting to unify physics, proposes the existence of 10 to the 500 possible universes, a number so large it dwarfs every atom in our observable cosmos. In this view, the fundamental constants of nature, the strength of gravity, the mass of electrons aren't finely tuned for life by chance, but simply the local bylaws of our particular cosmic neighborhood. Some of these alternate universes might be stillborn, expanding too fast for matter to clump, or collapsing instantly into black holes. Others could harbor exotic life forms built from entirely different particles. A sobering thought: if the multiverse is real, there might exist versions of reality where the Big Bang never happened at all, where space and time remain eternally dormant, never waking to the spark of creation. Critics argue this is untestable metaphysics, not science. But intriguingly, there might be ways to peek beyond our cosmic horizon. If another universe collided with ours in the distant past, the impact could have left scars in the cosmic microwave background, subtle temperature variations we might one day detect. Others suggest that quantum experiments could reveal tiny, tunneling effects where particles momentarily interact with parallel realities. Whether the multiverse is a mathematical curiosity or a fundamental truth, it reshapes our understanding of existence. If true, our universe's journey from chaos to cosmos wasn't unique, just one thread in an infinite tapestry of possibilities. And somewhere in that vast ensemble, another version of you might be pondering these same questions, gazing at a different night sky, wondering if they too are alone. The universe sprawls across billions of light years, dotted with trillions of planets, so many worlds that statistically, intelligent life should have arisen countless times. Yet when we listen for alien signals or scan distant exoplanets for signs of technology, we hear only silence. This eerie absence is the Fermi Paradox, the unsettling gap between the high probability of extraterrestrial civilizations and the total lack of evidence they exist. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a lunchtime conversation in 1950, this question cuts to the heart of our cosmic loneliness. One possibility is simple but chilling. Life might be vanishingly rare. Even with countless planets in habitable zones, the leap from chemistry to biology could require such precise conditions that Earth is a statistical fluke. Imagine winning the lottery 100 times in a row. That's the kind of luck some scientists propose was needed for DNA to form. Other worlds might host microbes or simple creatures, but intelligent, tool-using civilizations could be rarer than diamonds in a desert. Then there's the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar travel. This could be a natural hurdle, like the near impossibility of multicellular evolution, or something more sinister. Perhaps every advanced civilization hits a technological wall, nuclear war, runaway AI, ecological collapse, that wipes them out before they can spread beyond their home planet. If true, humanity's window of opportunity might be narrower than we think, but not all explanations are so grim. Some suggest aliens might be deliberately avoiding us, treating Earth like a nature preserve in a galactic zoo. Or communication could be the issue. Advanced societies might use technologies beyond our comprehension. Their signals as invisible to us as radio waves would be to medieval farmers. Imagine ants at a picnic, unaware of the human conversations happening above them. There's also the timescale problem. The universe is 13.8 billion years old, but hominids have existed for mere millions. If other civilizations arose even slightly earlier, they could have come and gone long before Earth formed, leaving behind ruins swallowed by cosmic time. Spacefaring species might be like ships passing in an endless night, their lifespans too brief to overlap. Yet the silence might not be absolute. SETI, the search for extraterrestrial intelligence, has only scanned a fraction of the radio spectrum, and new telescopes like the James Webb could spot biosignatures in exoplanet atmospheres. Breakthroughs in AI might help us decode potential signals or even recognize non-technological markers of intelligence like altered planetary chemistry. The Fermi Paradox forces us to confront two equally humbling truths. Either we're miraculously alone or we're hopelessly outmatched. Both possibilities rewrite humanity's place in the cosmos. But perhaps the greatest lesson isn't about aliens at all, it's about us. Every time we look up at the stars and wonder where everyone is, we're really asking how fragile, how precious, and how fleeting intelligent life might be. And that realization could be the key to ensuring our story doesn't end with a silent question mark. The universe seems to play by rules so precise they border on the miraculous. Tweak just one fundamental constant, the strength of gravity, the mass of an electron, the nuclear force that binds atoms, and the entire cosmic house of cards collapses. Make gravity a fraction stronger, and stars would burn through their fuel in millions rather than billions of years, leaving no time for planets, let alone life, to evolve. Weaken it slightly, and matter would never clump into galaxies at all. Even the seemingly arbitrary number that governs how tightly atomic nuclei hold together the strong nuclear force has to be balanced on a razor's edge. Increase it by just 2%, and hydrogen would fuse so rapidly in stars that water, the very solvent of life, might never exist. Decrease it by 5%, and protons couldn't bond into stable elements at all. This eerie precision isn't limited to a handful of constants. Over 30 distinct parameters, from the ratio of electron to proton mass to the energy density of empty space, must align with ludicrous accuracy for complexity to emerge. It's as if someone dialed in a cosmic combination lock, each number set to within a hair's breadth of perfection. Astronomer Fred Hoyle famously stumbled upon one such coincidence when studying how stars forge carbon. The process required carbon nuclei to resonate at an exact energy level, one that, against all odds, matched the conditions inside stellar furnaces. Hoyle later admitted that the odds seemed so improbable, it felt as if a super-intellect had monkeyed with physics. Scientists call this observation the anthropic principle, the idea that the universe's laws appear fine-tuned because, well, we're here to notice them. In its weakest form, it's almost a tautology. Of course, we find ourselves in a universe capable of producing observers, but the principle's stronger interpretations venture into profound territory. Some theorists propose that what we call the universe might actually be one bubble in a vast multiverse foam, each with randomly dialed physical constants. Most would be stillborn or barren, but a rare few by sheer statistics would hit the jackpot of life-friendly parameters. We'd inevitably find ourselves in one of those lucky outliers, no divine fine-tuner required. Critics argue this just kicks the mystery upstairs. What, then, determines the multiverse's rules? But supporters counter that it's no more speculative than invoking a single, inexplicably perfect universe. Meanwhile, an even more radical idea whispers at the edges of physics. What if the constants aren't truly constant? Some unified theories suggest that what we perceive as fixed numbers might be frozen artifacts of how our cosmic bubble formed, like cracks in ice preserving the shape of long-vanished water molecules. If true, the apparent fine-tuning could be a local illusion, with other regions of reality operating under entirely different bylaws. Yet for all the debate, the anthropic principle's greatest gift might be humility. It reminds us that physics isn't just about how the universe behaves, it's about why this particular universe behaves this way at all. Every time we measure a fundamental constant with greater precision, we're not just collecting data, we're reading the cryptic user manual of reality, searching for clues about whether our existence is inevitable, accidental, or something stranger still. And until we know for sure, the night sky remains both a mirror and a riddle, reflecting back the most unsettling question of all. Are the laws of nature written in stone, or are we just reading our own address in the cosmic fine print? Time moves in only one direction forward, like an arrow shot into the void, never to return. But why? The answer isn't found in clocks or calendars, but in something far more fundamental: entropy, the universe's relentless march toward disorder. Picture a sandcastle on a beach. Left alone, it doesn't stay pristine, it crumbles, its grains scattering in the wind. That's entropy in action, the natural tendency of things to fall apart, to dissolve from order into chaos. And it's this irreversible slide that gives time its direction, its unshakable forward momentum. The early universe was a rare exception to this rule, a singular moment of near-perfect order. Imagine a deck of cards freshly opened, every suit in sequence, kings followed by queens, aces aligned. That was the cosmos in its first moments, all energy packed into an unfathomably dense, uniform point. But with the Big Bang, that deck was violently shuffled. Space expanded, particles collided, and the universe began its slow, inevitable drift toward disorder. Every star that forms, every galaxy that spins, even the coffee cooling on your desk, they're all part of this grand unraveling, this cosmic progression from tight-knit symmetry to sprawling chaos. What's fascinating is how deeply this ties into our everyday experience. You can stir cream into coffee, but you can't unstir it. You can shatter a glass, but the pieces won't leap back together. These aren't just quirks of reality, they're reflections of entropy's one-way street. Even memories rely on it. Your brain records the past because energy dissipates as heat, leaving imprints that can't be undone. Without entropy, time would lose its meaning. Cause and effect would blur into a jumble of reversible events, like a movie played backward and forward at random. But here's the twist. Entropy doesn't just dictate time's flow, it shapes the universe's very structure. Stars shine because gravity pulls matter together, creating pockets of order. But that process releases heat, spreading energy outward and increasing the universe's overall disorder. Life itself is a temporary rebellion against entropy, a fleeting eddy in the cosmic current where energy is harnessed to build complexity. Yet even life ultimately pays entropy's toll as organisms break down and return to the chaos from which they came. Some theories suggest that if the universe ever collapses back into a big crunch, entropy might reset, reversing time's arrow. But for now, in this expanding, cooling cosmos, disorder only grows. And that's why yesterday is always behind us, why we remember the past but not the future, because entropy is the invisible hand guiding the universe's story, one irreversible moment at a time. So the next time you watch steam rise from a cup or leaves scatter in the wind, remember, you're not just seeing physics in action, you're witnessing time itself flowing inexorably forward, carried on the current of entropy's unyielding tide. The universe doesn't end with a bang or a crunch, but with a whisper. Imagine a cosmic graveyard where galaxies, now dark and lifeless, drift so far apart that even their light can no longer bridge the gap. Stars, once brilliant beacons, have burned through their fuel and faded to cold embers. Black holes, the last survivors, slowly evaporate into faint puffs of radiation. Space itself stretches thinner and colder until even time loses meaning, its passage marked only by the occasional flicker of a lone proton decaying into nothingness. This is the heat death, not an explosive finale, but an endless, silent unraveling. What makes this scenario so haunting is its inevitability, if dark energy continues its unchecked acceleration. Every galaxy beyond our local group will eventually vanish beyond an unreachable horizon, their light stretched to wavelengths too long to detect. Star formation will sputter out as gas clouds are torn apart by expansion, leaving the universe with only dwindling red dwarfs glowing faintly for trillions of years. Even those will eventually exhaust their fuel, leaving behind stellar corpses, white dwarfs cooling like dying coals, neutron stars spinning slower and slower until they freeze solid. The last flickers of heat will dissipate into the void, and the temperature of the cosmos will approach absolute zero, a state where even atomic motion ceases. But here's the twist: this bleak fate isn't guaranteed. The nature of dark energy remains one of physics' greatest mysteries. If it weakens over time, gravity might regain dominance, pulling the universe back toward a possible collapse. Or dark energy could grow stronger, leading to a big rip, where even atoms are torn apart in the final moments. Some theories even suggest quantum fluctuations could spark a new Big Bang in the far future, resetting the cosmic clock. The heat death is merely the most straightforward projection, a default path if nothing unexpected intervenes. Yet the heat death's true significance isn't just about how the universe ends, it's about what it means for the story of existence. All complexity, all structure, even the memory of galaxies and civilizations, will fade into featureless equilibrium. It's a humbling reminder that the universe's most enduring legacy might not be permanence, but the fleeting moments of order and beauty that arose along the way. The stars that forged the atoms in your body, the galaxies that spun them into being, they were never meant to last forever. Their brilliance was always borrowed time, a temporary defiance of entropy's relentless pull. So while the heat death may loom in the unimaginably distant future, its shadow gives urgency to the present. Every discovery we make, every connection we forge, exists against the backdrop of a cosmos that won't remember us. And perhaps that's the most profound lesson of all. The universe doesn't owe us eternity, but here, now, in this narrow sliver of cosmic time, we get to witness, to explore, and to wonder. And that might be enough. The universe's final act might not be a slow fade to black. It could be a dramatic encore or a catastrophic finale. Imagine all the galaxies, stars, and planets not just drifting apart, but rushing back together in a cosmic reunion so violent it mirrors the Big Bang in reverse. This is the Big Crunch, a scenario where gravity, the same force that sculpted galaxies, finally overcomes dark energy's relentless push. After tens of billions of years of expansion, the universe would shudder to a halt, then collapse inward like a deflating balloon. Temperatures would soar as space contracts, galaxies merging in a firestorm of collisions until every atom is compressed into a singularity. It's a poetic symmetry, beginning and end fused into one, the universe swallowing its own tail. But here's the catch: for this to happen, dark energy, the mysterious force accelerating expansion, would need to weaken or reverse. Current observations suggest the opposite. Dark energy seems stubbornly constant, as if space itself is determined to keep stretching. Yet some theories propose that dark energy could decay over time, or that new physics might emerge at scales we can't yet probe. If so, the Big Crunch remains a tantalizing what if, a reminder that the universe's fate isn't set in stone. Now flip the script entirely. Instead of collapsing, what if the universe tears itself apart? This is the Big Rip, a nightmare scenario where dark energy grows stronger with time, accelerating expansion until it overwhelms every force that holds reality together. First, galaxy clusters would be ripped apart, then individual galaxies. Stars would detach from their orbits, planets from their stars. In the final moments, even atoms would be shredded as the space between particles expands faster than light can bridge the gap. Time and space would cease to function as we know them, leaving behind a fragmented, lifeless void where nothing can ever interact again. The key to these wildly different outcomes lies in dark energy's true nature. Is it a constant force, as Einstein's cosmological constant suggests, or does it evolve, growing stronger or weaker over time? Right now, telescopes like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope are mapping the universe's expansion with unprecedented precision, hunting for clues in the subtle way galaxies cluster and light bends across cosmic distances. Each new data point edges us closer to answering whether the cosmos will end with a collapse, a rip, or something stranger still. What's humbling is how much we don't know. The universe's destiny hinges on physics we've yet to uncover, perhaps hidden in the quantum foam of space-time or buried in the equations of a theory that unifies gravity and quantum mechanics. Until then, the Big Crunch and Big Rip stand as twin reminders of how fragile our cosmic order really is. One thing's certain: the universe's story won't end quietly. It'll be a finale written in the language of forces we're only beginning to understand. Every atom in your body has a cosmic backstory older than the Earth itself. That oxygen you're breathing right now, forged in the heart of a massive star that died billions of years before our solar system formed, the iron in your blood. Created in the final violent moments of a supernova explosion, then hurled across interstellar space until it found its way into the cloud of gas that would become our sun and planets. Even the calcium in your bones was once stardust floating for eons before becoming part of you. This isn't poetic metaphor, it's established science. Stars are the universe's ultimate alchemists, transforming simple hydrogen and helium into heavier elements through nuclear fusion. smaller stars like our Sun can produce elements up to carbon and oxygen during their stable lifetimes. But the real heavy element factories are the massive stars that end their lives in spectacular supernova. In those final cataclysmic seconds, temperatures reach billions of degrees, creating everything from the silicon in rocks to the gold in jewelry. The explosion then scatters these newly forged elements across light years, seeding future generations of stars and planets with the building blocks of complexity. What's astonishing is the journey these atoms took to reach us. After being ejected from their stellar nurseries, many became part of vast molecular clouds, cosmic recycling centers where new stars form. Our own solar system condensed from such a cloud, enriched by multiple generations of stars. Some meteorites still contain microscopic stardust grains older than the Sun, tiny time capsules from the universe's early chemical factories. When you hold a piece of iron, you're literally holding material that survived the violent death of a star, traveled through space, and was present at Earth's formation. This profound connection changes how we see ourselves. The traditional boundaries between astronomy and biology blur when you realize that the same calcium that forms your bones also makes up the shells of sea creatures and the limestone of ancient cliffs, all originally forged in stars. The nitrogen in your DNA, the phosphorus in your ATP energy molecules, even the zinc in your enzymes, all were stellar products before becoming biological ingredients. Modern technology lets us trace this cosmic ancestry with precision. Mass spectrometers can identify the distinctive isotopic signatures of elements from different types of stellar explosions. Astronomers have even observed the chemical enrichment of galaxies in real time, watching as supernova eject heavy elements that will eventually become part of new planetary systems. We're not just observers of this process, we're products of it, living proof that the universe can transform primordial hydrogen into conscious beings over billions of years. Perhaps most remarkably, this stardust connection isn't unique to Earth. Every rocky planet in the cosmos shares this stellar heritage. The same processes that created our elements would operate similarly across the universe, meaning alien life, if it exists, would also be built from recycled star material. When we search for exoplanets with the right chemistry for life, we're essentially looking for other places where stardust had the right conditions to assemble into complexity. So the next time you look up at the night sky, remember, you're not just observing distant stars, you're seeing your extended family. Those twinkling lights are the ancestors of every atom in your body, the great cosmic forges that made your existence possible. We may be temporary collections of these particles, but the stardust itself is immortal, continuously reshaped into new forms across the eons. In the most literal sense possible, we are the universe becoming aware of itself. Among the countless stars that light up the night sky, many hide secrets more astonishing than fiction, worlds beyond our solar system, each with its own story. These exoplanets, some rocky like Earth, others gaseous giants or frozen wastelands, orbit distant suns in configurations that challenge our imagination. What makes them truly extraordinary isn't just their existence, but the possibility that some might cradle the most precious cosmic rarity of all, life. Consider Kepler 186f, a planet 500 light-years away, sitting snugly in its star's habitable zone, that Goldilocks region where temperatures are just right for liquid water. It's not alone. The TRAPPIST-1 system boasts 7 Earth-sized planets, 3 of which dance in orbits where water could flow. These aren't just scientific curiosities, they're testaments to the universe's relentless creativity. If chaos birthed our solar system, then the same turbulent processes must have sculpted countless others, each with its own chance at fostering life. But finding these worlds isn't simple. planets don't announce themselves with blazing light. They're faint shadows against the glare of their stars. Astronomers hunt them using ingenious methods like the transit technique, where a planet's silhouette dims its star's light as it passes, or the wobble method, which detects a star's subtle dance as an orbiting planet's gravity tugs it back and forth. These techniques have revealed over 5,000 confirmed exoplanets, with estimates suggesting hundreds of billions more in our galaxy alone. The James Webb Space Telescope is revolutionizing this search. With infrared eyes, it peers through cosmic dust to analyze exoplanet atmospheres, sniffing for chemical fingerprints like oxygen, methane, or even industrial pollutants. Imagine detecting a world with an atmosphere rich in oxygen and water vapor, a cocktail that on Earth signals life's relentless activity. Such a discovery wouldn't just answer whether we're alone. It would reveal that the universe doesn't just build stars and galaxies. It cultivates life as naturally as a garden grows flowers. Yet the search isn't just about spotting Earth twins. Exoplanets stretch our understanding of habitability. Take tidally locked worlds where one side eternally faces its star, broiling under perpetual daylight, while the other freezes in endless night. Could life cling to existence in the twilight between? Or water worlds, entire planets drowned in oceans hundreds of miles deep, might hydrothermal vents there brew exotic life forms unlike anything on Earth? Even rogue planets untethered to any star drifting through interstellar space, could subterranean oceans warmed by radioactive decay harbor life in absolute darkness? The implications are staggering. If life thrives elsewhere, it would mean the universe is hardwired for complexity, that given the right conditions, chaos inevitably gives rise to cosmos. But if we search and find nothing, that silence would speak volumes, suggesting Earth might be a statistical miracle in an otherwise barren expanse. Either way, the hunt for exoplanets isn't just about discovering new worlds. It's about understanding our place in the grand tapestry of existence. And with every new planet found, we're one step closer to knowing whether the story of life is a solitary chapter or a saga written across the stars. Picture a tiny microbe no larger than a grain of pollen, frozen in the heart of a comet hurtling through the void between stars. This isn't science fiction. It's the bold claim of Panspermia, the theory that life might not have originated on Earth at all, but instead arrived here as a cosmic stowaway. The idea stretches back to ancient Greece, but modern science has given it startling credibility. We now know that space is far from sterile. Meteorites like the Murchison specimen, which fell in Australia in 1969, contain amino acids, the building blocks of proteins, proving that the raw ingredients for life can survive interstellar journeys. What makes Panspermia so compelling isn't just the possibility of life's interstellar travel, but the mechanisms that could make it happen. When a massive asteroid slams into a planet like Mars, the impact can blast debris and any hardy microbes clinging to it into space at escape velocity. These rocky fragments become nomadic vessels, drifting for millions of years until gravity pulls them toward another world. Experiments on the International Space Station have shown that certain bacteria, like Deinococcus radiodurans, can survive years of exposure to the vacuum, radiation, and temperature extremes of space. Tardigrades, those microscopic water bears, go even further, entering a death-like state called cryptobiosis that lets them withstand conditions that would obliterate most life forms. The implications are staggering. If life can hop between planets, then Earth may not be its only home. Microbes ejected from early Mars could have seeded our planet during the late heavy bombardment 4 billion years ago, when asteroid impacts were frequent. Europa's subsurface ocean or Enceladus's icy plumes might harbor life that shares a common ancestor with Earth's, not because of convergent evolution, but because they're literal relatives separated by cosmic distances. Even interstellar panspermia isn't off the table. Giant molecular clouds, the birthplaces of stars, could act as galactic waste stations, trapping and transporting microbes across light years within comet-like life rafts shielded by layers of ice. Critics argue that panspermia merely shifts the origin question elsewhere. How did life start in the first place? But proponents counter that it expands life's potential habitats exponentially. If life arose just once in a stellar system like TRAPPIST-1, with its 7 Earth-sized planets packed close together, interplanetary transfer would be almost inevitable. Even more radical is the idea of directed panspermia, the notion that an advanced civilization might deliberately seed lifeless worlds with microbes, a concept championed by astronomers like Fred Hoyle and Francis Crick. The search for evidence is already underway. When the OSIRIS-REx mission returned samples from asteroid Bennu in 2023, scientists scrutinized them not just for chemistry, but for any hint of fossilized microbes. Future missions to Mars or Europa might look for genetic markers that could trace life back to a common source. And if we ever find life with DNA eerily similar to Earth's, it won't just rewrite biology textbooks, it'll prove we're all citizens of a much larger, interconnected biosphere, one that spans not just continents but solar systems. Panspermia turns the cosmos into a vast network of possibility, where life isn't bound to a single world, but could spread like dandelion seeds on the solar wind. Whether it's true or not, the theory reminds us that Earth isn't an island, but part of a dynamic, messy, and astonishingly creative universe, one where the story of life might be written across the stars themselves. Imagine crushing the entire mass of our Sun into a sphere no wider than Manhattan. The result isn't a black hole, not quite, but something almost as bizarre, a neutron star, nature's most extreme physics laboratory. These stellar corpses are born from the violent deaths of massive stars, their cores collapsing under gravity's irresistible pull until protons and electrons merge into neutrons, packing matter tighter than anywhere else in the known universe. A single sugar cube-sized chunk of neutron star material would weigh as much as Mount Everest, so dense that its gravity bends light into a visible halo around it. What makes neutron stars truly remarkable isn't just their density, but the extreme environments they create. Magnetic fields around these objects can reach 1,000,000 billion times stronger than Earth's, so powerful they distort the very structure of atoms in their vicinity. Surface temperatures exceed 1,000,000 degrees, while their cores may harbor exotic states of matter we can't replicate anywhere on Earth. Some theories suggest the pressure there might squeeze neutrons into a Quark-Gluon Plasma, a primordial soup last seen microseconds after the Big Bang. Others propose even stranger possibilities, like superfluids that flow without friction or crystalline neutron pasta, with shapes resembling spaghetti and lasagna sheets. These cosmic extremophiles don't just tease physicists with their mysteries, they actively help solve them. When 2 neutron stars collided in 2017, the resulting gravitational waves and gamma-ray burst allowed scientists to confirm where heavy elements like gold and platinum are forged. The event created ripples in space-time detectable across 100 million light-years, while scattering enough precious metals to seed future solar systems. It was a smoking gun for theories about cosmic alchemy, proving that the universe's jewelry box is filled through stellar cataclysms. Neutron stars also serve as nature's precision instruments. Pulsars, rapidly spinning neutron stars that beam radiation like cosmic lighthouses, keep time more accurately than atomic clocks. Their pulses are so regular that astronomers use them to confirm Einstein's theory of general relativity by measuring how their signals warp near massive objects. Some millisecond pulsars complete hundreds of rotations every second, their surfaces moving at nearly a quarter the speed of light without flying apart, a testament to unimaginable gravitational binding. Yet perhaps their greatest gift is how they push our understanding to the breaking point. At neutron star densities, familiar physics starts behaving strangely. Electrons tunnel through barriers they shouldn't penetrate. Heat flows in ways that defy classical thermodynamics. Even the concept of an element blurs as atomic nuclei dissolve into a quantum sea of neutrons. Studying these anomalies helps scientists refine theories about everything from nuclear physics to the nature of spacetime itself. So while black holes suck up all the cosmic glamour, neutron stars do the quiet, groundbreaking work of revealing how matter behaves when pushed to its limits. They are proof that sometimes the universe's most profound lessons come not from the voids, but from the unimaginably dense kernels of existence left behind when stars burn out. And every time we detect their faint pulses across interstellar space, we're eavesdropping on nature's most extreme experiment in progress. White dwarfs are the universe's quiet retirees, stellar pensioners that have burned through their nuclear fuel and settled into a slow, dignified fade. Unlike their more dramatic cousins, the neutron stars and black holes, white dwarfs don't end with a bang or a collapse into oblivion. They simply stop. After shining for billions of years, stars like our sun exhaust their hydrogen, then helium, puffing up into red giants before shedding their outer layers in shimmering planetary nebulae. What remains is a core about the size of Earth, but with a mass comparable to the sun. A teaspoon of this material would weigh as much as an elephant. These cosmic embers are held up not by nuclear fusion, but by quantum mechanics. The electrons in a white dwarf are packed so tightly they resist further compression through a phenomenon called electron degeneracy pressure. It's as if the star's core becomes a sea of electrons pushing back against gravity's relentless squeeze. But this standoff isn't eternal. Over trillions of years, timescales longer than the current age of the universe, white dwarfs will radiate away their remaining heat, dimming from white to yellow, then red, and finally to invisible black dwarfs. The universe isn't old enough for any black dwarfs to exist yet, but given enough time, even these faint remnants will crystallize into massive spheres of diamond like carbon and oxygen, floating in the eternal dark. What makes white dwarfs fascinating isn't just their fate, it's what they reveal about stellar life cycles. Their composition is like a cosmic autopsy report, telling us what elements the star fused during its lifetime. Some are carbon-rich, others oxygen-dominated, with traces of heavier elements dredged up from their depths or accreted from interstellar debris. A few even sport rings or debris disks, the remains of planets that survived their star's red giant phase only to be torn apart by tidal forces. The discovery of polluted white dwarfs, those with unexpected elements like calcium or iron in their atmospheres, suggests they're actively consuming their own planetary systems, offering a grim preview of what might await Earth when the Sun reaches this stage. Yet white dwarfs aren't just tombstones, they're also cosmic timekeepers. Because they cool at predictable rates, astronomers can use them as chronometers to estimate the age of star clusters and even the Milky Way itself. The oldest white dwarfs in our galaxy act like cosmic hourglasses, their faint glow hinting at when the first stars began to fade. And in binary systems, they sometimes steal material from companion stars, flaring up as nova or even detonating as Type I supernova, the standard candles that helped astronomers discover dark energy. Perhaps most poetic is the idea that these stellar remnants will outlast nearly everything else. Long after the last stars have burned out and galaxies have drifted apart, white dwarfs will still be there, cold and dark, serving as the universe's final monuments to the age of light. They remind us that even in the cosmos, not all endings are violent. Some are slow, silent, and strangely beautiful. Galaxies don't just grow quietly over time. They devour their neighbors in a celestial feast that reshapes the cosmos. Picture a vast cosmic food chain where the largest galaxies, like Andromeda and our own Milky Way, act as apex predators, consuming smaller satellite galaxies in a process astronomers call galactic cannibalism. These mergers aren't tidy affairs. Gravity pulls smaller galaxies apart, stretching them into luminous streams of stars that orbit their captors like cosmic spaghetti. The Milky Way's halo still bears the scars of past meals, ghostly remnants like the Sagittarius dwarf spheroidal, a galaxy currently being torn apart and absorbed into our own. What's astonishing is how common this process is. Nearly every large galaxy we've observed shows signs of past mergers. Andromeda, our closest galactic neighbor, sports vast shells of stars, ripples from ancient collisions, and its outskirts are littered with stellar debris from devoured companions. Even the majestic Pinwheel galaxy, with its perfect spiral arms, likely grew by swallowing smaller galaxies over billions of years. These mergers aren't destruction, they're transformation. When galaxies collide, their gas clouds slam together, triggering bursts of star formation that light up the cosmos like fireworks. The violence stirs the interstellar medium, enriching it with heavy elements forged in supernova, ensuring future generations of stars have the building blocks for planets and potentially life. But the most dramatic merger of all still lies ahead. In about 4.5 billion years, the Milky Way and Andromeda will collide in a slow-motion dance lasting millions of years. Computer simulations show the two spirals first brushing past each other, their mutual gravity warping their shapes into grotesque, tangled forms. Stars will be flung into wild new orbits, though the vast distances between the mean stellar collisions are unlikely. Eventually, the galaxies will merge into a single, massive elliptical galaxy astronomers nicknamed Milkdromeda. The night sky from any surviving planets will be utterly transformed, no familiar Milky Way band, but a dazzling, chaotic sprawl of stars from two merged civilizations. Yet this process isn't unique to our local group. Across the universe, galaxy clusters showcase the aftermath of these cosmic battles. The Virgo cluster, 54 million light-years away, contains shell galaxies with concentric rings of stars, like tree rings marking growth spurts from past mergers. Even more extreme, the Tadpole galaxy sports a tail of stars 300,000 light-years long, a smoking gun of a recent collision. These events aren't just spectacular, they're essential. Without galactic cannibalism, the universe would lack the giant elliptical galaxies that anchor galaxy clusters, and spirals like ours might never have grown large enough to foster stable planetary systems. So while the thought of galaxies consuming one another might sound violent, it's really the universe's way of recycling on the grandest scale. Every time you look up at the Milky Way, you're seeing the accumulated legacy of countless mergers, a cosmic family tree written in starlight. And when Milkdromeda finally forms, it won't be an ending, just the next chapter in an epic story of growth, change, and rebirth that's been unfolding since the dawn of time. At the heart of modern physics lies a paradox so profound it keeps scientists awake at night, two wildly successful theories that refuse to speak the same language. On one side, quantum mechanics predicts the behavior of subatomic particles with breathtaking precision, governing everything from the glow of a light bulb to the silicon in your smartphone. On the other, Einstein's general relativity describes the cosmic dance of planets, stars, and galaxies with equal elegance. Yet when these two meet, at the edge of a black hole or the instant of the Big Bang, their equations explode into nonsense. It's as if the universe wrote separate rule books for the very small and the very large, then dared us to find the missing page that connects them. Enter the holy grail of physics, the theory of everything. This isn't just about tidying up equations, it's about uncovering the fundamental language of reality itself. Imagine discovering that quarks and supernova, atoms and galaxies, are all notes in a single cosmic symphony, played on strings of energy or woven into a fabric of space-time loops. The implications would rewrite our understanding of existence, answering questions we haven't even thought to ask yet. How did the universe truly begin? What happens inside a black hole's singularity? Could extra dimensions lie curled up tighter than an atom, hidden in plain sight? String theory has long been the frontrunner in this quest. It proposes that all particles are microscopic vibrating strings with different harmonies corresponding to electrons, photons, and the rest of nature's building blocks. The math is beautiful until you realize it requires 10 or 11 dimensions to work, 6 or 7 of which are compacted into spaces smaller than we could ever probe. Then there's loop quantum gravity, which reimagines spacetime as a network of interwoven threads, solving the quantum gravity puzzle without extra dimensions but struggling to incorporate other forces. Both approaches have spent decades in a stalemate, each explaining certain phenomena while leaving others frustratingly out of reach. Yet the search continues because the payoff would be staggering. A true theory of everything wouldn't just reconcile quantum mechanics and gravity. It could explain why the universe has precisely the right constants to allow stars, planets, and life itself. It might reveal whether time truly flows or is an illusion, whether parallel universes exist, or if information can escape black holes. Some theories even suggest that spacetime itself could emerge from deeper, more fundamental structures, like temperature arising from the motion of atoms. The challenge isn't just mathematical, it's philosophical. How do we test ideas that operate at energies 1 trillion times beyond what our particle colliders can reach? Some scientists scour the cosmic microwave background for imprints of quantum gravity. Others hunt for subtle deviations in how neutron stars warp spacetime. There's even hope that black hole mergers detected through gravitational waves might betray hints of physics beyond Einstein's equations. What keeps physicists going isn't just the promise of answers, it's the thrill of the unknown. Every failed experiment, every stubborn inconsistency is a clue waiting to be decoded. And when the breakthrough finally comes, it won't just be a footnote in a textbook. It'll be the moment humanity peers behind the curtain of reality, discovering whether the universe is a cosmic accident, a mathematical necessity, or something stranger still. Until then, the search itself, with all its dead ends and dazzling possibilities, remains one of science's greatest adventures. From the unimaginable heat of the Big Bang to the delicate cosmic web we see today, the universe has performed a magic trick of staggering proportions, turning pure chaos into intricate order. Those first turbulent moments weren't just random violence. They were the crucible that forged every galaxy, every star, and every atom in your body. The same quantum fluctuations that made matter clump together also set the stage for life to emerge billions of years later. It's as if the universe wrote its own recipe for complexity in those first chaotic seconds, with just the right amount of disorder to prevent stagnation and just enough structure to build something beautiful. What's truly humbling is how deeply we're woven into this story. The carbon in your DNA, the iron in your blood, even the calcium in your bones, all were forged in stellar furnaces and scattered across space by supernova and galactic collisions. When you look up at the night sky, you're not just observing distant objects, you're seeing the chain of events that made your existence possible. Those spiral arms of the Milky Way aren't just pretty patterns, they're the gravitational whirlpools that gathered the material for our solar system. The very laws of physics seem fine-tuned to allow atoms to assemble into molecules, stars to shine for billions of years, and planets to provide stable homes for life. Yet for all we've uncovered, the universe still guards its deepest secrets. Dark matter's invisible grip continues to shape galaxies we can't fully explain. Dark energy's mysterious push accelerates the cosmos toward an uncertain fate. Even the humble neutrino, a ghostly particle that streams through your body by the trillions every second, defies simple understanding, oscillating between identities as it travels near light speed. Each mystery solved seems to reveal three more, like peeling an infinite cosmic onion. This isn't the end of the story, it's barely the beginning. New telescopes peer deeper into space and further back in time than ever before. Gravitational wave detectors listen for the faintest ripples in space-time. Particle colliders recreate conditions not seen since the universe's first trillionth of a second. With every tool we build, we gain new ways to read the universe's autobiography, written in the language of gravity, light, and quantum uncertainty. The journey from chaos to cosmos didn't stop with the formation of galaxies or the birth of stars. It's happening right now, in the laboratories and observatories where curious minds piece together the puzzle of existence. And when you step outside on a clear night, gazing up at those countless points of light, remember, you're not just a spectator to this grand narrative. You're a living chapter in the universe's ongoing story, one that's still being written, one discovery